I think our next presenter doesn't need much of introduction, not only because Professor Bahnfleth is the chair of the epidemic task force for ASHRAE, so the epidemic task force was very known because it did a tremendously very good job informing everybody and having very useful information about the epidemic task force. But apart from that, we had the honor of having Professor Bahnfleth in quite a few of our events, and he was very kind to pay us a couple of visits in the past. So we would like to thank him once again for being here and presenting for us. And I will make you a presenter so we can have your presentation. Thank you very much.
I've seen that you posted responses to some of the questions, Bill. Good afternoon from Athens, from sunny Athens. How are you?
Yes, I did add a few of my own thoughts to those.
We can go through them after the end of your presentation, if that's okay with you.
Sure. Am I showing the correct screen now?
Yep. You're
All right, great.
Okay.
So,
okay, the floor is yours.
Yeah, thank you for the invitation to join you today. I do wish I could be there in person. I actually didn't look at the program until last night when I started working on my talk, and I was glad to see that Sonia was going to cover a lot of the things that I normally talk about in the presentations I do. I've done roughly 110 talks on COVID since last March, usually 2 or 3 a week, and I'm glad to have free reign to talk about some other related issues without having to go through all of those basics. So I put together a talk that really tries to focus our thoughts not just on reopening, but on what the future should be like after the pandemic. And it's not the usual kind of presentation I give, but I hope that you'll find something useful in it, and I'm happy to answer as many questions as you have time for after it's over. So, as I said, it would certainly be nice to be in Greece. This is a photo from my last visit, which was to both Athens and Thessaloniki, where I went for the conference and presented there with Dennis Knight a couple of years ago. The last time I was on an airplane was on March 15th last year, and I have literally not traveled anywhere since then. So it's been an interesting 12 months with the entire world shut down by this pandemic that we're dealing with. And when I started thinking about what I would talk about, I really went back to some thoughts about how long we have been talking about the need for better air quality in buildings, and for how long we've been not dealing with it. And so if you'll indulge me, I before getting into technical matters very far, put together a few slides just to give an idea of what the history of this issue is. Some may remember that my father was the president of ASHRAE in 1985-86, and one of the interesting things about his term in office was that was the year that the ASHRAE Environmental Health Committee was created, and that was the year that the IAQ conference that ASHRAE has put on now 18 times was started. The next one, God willing, will be in Athens in September of this coming year. So I found this quote several years ago when I was putting together a keynote address for one of the IAQ conferences that came from his State of the Society speech in 1986. Indoor air quality will be the most important health concern we'll face for the remainder of the 20th century. And that certainly has turned out to be right, although maybe he's off by a few years. It now looks like it will be the most important issue that we may face in the 21st century as well. So we have a very long history in our technical societies of trying to address indoor air quality, but it's been hard to get traction given the attention that's been paid, particularly to energy and atmosphere issues for some time, and also simply for because of the cost issues associated with air quality control. So if we go forward a few more years, it's been 20 years since there was really quite a bit of activity that got underway to document what the lost value was of good indoor environmental quality. Bill Fisk from the US, Lawrence Berkeley National Lab, did a large amount of very valuable research in this area, and he also collaborated with Olli Seppänen from Finland. And in a short article that was published in 2002, he summarized his estimates of the value lost every year from poor indoor environmental quality in the US that could be cost effectively addressed. And the total number doesn't matter so much, it's hundreds of billions of dollars, but it's interesting that this loss that we're enduring, really an externality though, because it's not quantified, nobody's actually paying for it in terms of paying a bill, was about the same as the total cost of energy that's used by buildings. So we've known about this for a long time, and Bill was by no means the only one who was making us aware of these issues. Now, ASHRAE's had an airborne infectious diseases position document since 2009. So that's now been 12 years that ASHRAE raised this to the level of a society policy concern. And if you look at the names of the people who were on the original committee, some of them are still extremely active in this area. If you follow Twitter, Shelley Miller is there a lot talking about COVID. Hugo Lee really should also need no introduction. From Hong Kong, he's done a lot of work on infection transmission in buildings. And there are others as well, like Chandra Shekhar, who's from Singapore. So ASHRAE has been at least explaining that this is an important issue for a number of years. What we've done about it is another question. I started doing talks on the importance of air quality in 2012 after Walid Shakroun from Kuwait invited me to do a keynote at the ASHRAE conference. And this is the summary slide from that first presentation. My conclusions are a little bit different now, but the basic conclusion is that we have mediocre air quality in buildings, and we know it, and it's costing us a lot, and we know how to make it better, but we aren't doing it. So changes are needed. Now, that's been a consistent message that many have been delivering for quite a while now. So we still hadn't done anything. 2012, and buildings were about the same. In 2003, the original SARS epidemic came along, and Hugo Lee, among others, wrote the paper shown here that analyzed the Amoy Gardens apartment complex in Hong Kong and showed that SARS was airborne and that it was transmitted from building to building by air and from room to room by air movement and also through plumbing. So things that we've had to argue about again during the SARS-CoV-2 epidemic were all hashed about more than a decade ago, and all of this information is still there. We could have acted on it, but again, we didn't do much to make buildings better. So 2018 was the 100th anniversary of the so-called Spanish flu pandemic, really the worst one that's happened in modern times. And I just stumbled on this presentation last night. So in 2018, the Centers for Disease Control and Prevention in the US put on a program that included this presentation, Are We Ready for the Next Pandemic? And noted that we have better tools for responding, but that most countries aren't prepared. Slightly prophetic considering what happened just a few years later. Then here's the ASHRAE 2019-2024 strategic plan. We have two outward-facing objectives in this plan, and one is to improve the resilience of buildings and communities, and the other is to improve indoor environmental quality in buildings. So this was still before COVID-19, but ASHRAE had recognized and finally put into its strategic plan that these were really important issues to talk about. But then here we are today in the middle of this pandemic that so far has resulted globally in 128 million cases and almost 3 million deaths, and it's still cooking along quite vigorously. We keep thinking it's about over, but we've been thinking that since last spring and expected the summer to be the end of it all. So we're far from out of the woods yet. So that's my background to say that we've been aware of the need to do something for a long time, and we just haven't done it. And I wonder and hope whether the experience of the last year is going to be enough to really get us to the point of saying we're going to change the way buildings are designed and operated to make them safer and healthier for the people who are in them. So what have we learned so far during the pandemic? The first thing that I think is quite clear is that the indoor environments contribute to airborne disease transmission, and I'll show a few examples of that shortly. Another thing that I think is also quite clear, and I'll examine this as well, is that buildings don't provide enough protection against airborne infection. If they did, then you wouldn't have had to have Sonia give the presentation she just did about all the things that we can do to make buildings safer. And a related point is that buildings aren't resilient with respect to indoor air quality. They may be acceptable for normal conditions, but we've certainly found that when there are emergencies, whether they relate to indoor conditions like an epidemic or outdoor conditions like wildfires or other air quality events outdoors, that buildings aren't really able to respond very effectively. And we've certainly also found that we have many knowledge gaps about things that we probably thought were pretty well understood, but having to actually utilize some of the technologies that we're trying to utilize now, it's become clear that we have a long way to go in terms of building the knowledge base that we need. So as I mentioned, I was going to say something about how buildings participate in transmission. One of the issues that's been identified, and this was early on, was the effect of poor ventilation on transmission. So many will recognize this figure from an article about the Guangzhou restaurant incident that Hugo Lee and others studied. We had 9 people infected by one pre-symptomatic person during a Lunar New Year dinner, and they were all sitting in one area of this restaurant where the air was circulated by a ductless mini split type of air conditioner. No ventilation here, and the air leakage rate was measured at 1 liter per second per person or less. So factor of 7 to 10 lower than we would expect to have in a restaurant, and there were a lot of infections. So this was one of the early cases that was really pretty persuasive that airborne transmission of SARS-CoV-2 was going on. We also have evidence of the effect of bad air distribution, by which I mean poor airflow patterns in spaces causing infections. So this is a much more recent and very interesting study from a restaurant outbreak in South Korea. There was one person who was infected sitting against a wall here, and not surprisingly, that pre-symptomatic person's dining companion was infected, but in the whole restaurant, only 2 others were infected. And you can see their locations here, 6 to 7 meters away. An analysis of the risk factors in this restaurant revealed that probably the only factor that could be associated with these 2 people being infected was that the air conditioning units, assume these were VRF cassettes in the ceiling, were creating an airflow from the infector to these 2 people who became infected that had a velocity of as high as 1.2 meters per second. So that's 10 times or more higher than the ambient velocity we'd like to see in a overhead mixing type of situation. And to indicate, how significant this airflow pattern was, this person was only in the restaurant for 5 minutes with the infector, and the other one was there for 20 minutes, and that was verified by cell phone records as shown in the table here. A very interesting case study. So HVAC systems can be a factor when we have these airflow patterns, and that's why Sonia was talking about not using certain types of devices, or at least being careful about airflows in the occupied zone that can move contaminated air from one person to another. Uncontrolled airflows in buildings are also a risk factor. So another recent South Korean study found multiple infections in one apartment block, and what tied all of these apartments together were natural ventilation shafts that did not have backdraft dampers on them. So depending on the temperature conditions, you could have upflow or downflow in these shafts, and you could have reentry from the shaft into an apartment. And that's the only factor that was implicated in more than 10 infections in this case. And yet one more, here's another case that's reminiscent of the original SARS outbreak, another Korean apartment building, and evidence of fecal aerosol transmission. So someone uses a toilet, they found an index patient in one apartment, and there were multiple infections in other apartments on different levels. So the mode of transmission was apparently fecal aerosol that either through the that got into the vent and re-entered other apartments through dry traps, which seems to be a problem in some parts of the world. So we've seen a lot of different ways in which buildings can influence transmission. Let's move on from that to the question of whether our standards for building design are sufficient or not if we're concerned about infection control. Sonia showed this definition of acceptable indoor air quality. It comes from ASHRAE standard 62.1. I'm showing it again to point out that this doesn't say anything about infection control. So what our standards, and this would apply to standards in other countries as well, tend to focus on is building generated contaminants, no known contaminants at harmful concentrations. That means we have to actually know they're there, and there has to be a known level of concern, and typically we don't measure anything in a building after it's constructed. And the other factor is acceptability to occupants, so essentially an odor criterion. And so we have ventilation rates that in minimum standards at the lowest class of European standards, or in ASHRAE standard 62.1, which only has a single level, we're talking about 7.5 liters per second per person, which research done by Oli Fanger at DTU and others results in about 20% dissatisfaction. And that's far less than the ventilation rates that are specified in standards that are written for healthcare facilities. Those might be 2 or 3 or 4 times the amount of outdoor air that's required for a non-healthcare facility. And in addition, there are higher filtration requirements there, which is the next thing that we'll come to. So the direction that ASHRAE standard 62.1 is moving is to more of a performance basis, although the definition of acceptable indoor air quality hasn't changed. You may be aware that there's an addendum that's been under consideration for several years that will completely replace the existing indoor air quality procedure, which puts it on the designer to determine which contaminants need to be investigated, and replace that with a list of design compounds and PM 2.5 for which standards are established. And a building that is using the IAQ procedure will have to meet all of these criteria, and they all have to be verified objectively after the building is constructed. But notice that there's nothing here about microorganisms. So this still doesn't address the issue of infection control, and there's not necessarily a connection between ventilation rates that would be sufficient to control these contaminants and ventilation rates that would be sufficient to control infection risk. There are also some requirements for looking at mixtures. That's just a fine point that I won't dwell on here. So that's the basis, and we have lots of evidence that I show in some of my other talks that these minimum ventilation rates are far from optimal in just about any sense that you want to look at them. So on the left here is some results of studies that were compiled by Fisk and his colleagues that show that sick building syndrome incidence can be dramatically reduced by increasing ventilation rates by a factor of 2 or more beyond where they are now. So the reference point here is 10 liters per second per person. And if we go from there to 20 liters per second per person, there's a 20% reduction on average from all of these studies in sick building syndrome symptoms. Similarly, Sepinen and Fisk collaborated to produce this study of effect on task performance of ventilation rate and found, again, that doubling or tripling the ventilation rate above minimum levels could result in 3 or 4% improvement in productivity. So this is some of that data from 20 years or more past that pretty clearly indicates that our ventilation rates are lower than they need to be, and that's not even considering infection risk. So let's go on and talk about filters a little bit here now. Again, reference was made in the previous talk to mechanical filters and the MERV rating system. ASHRAE standard 52.2 is used in the US. We can roughly equate some of the MERV ratings to the ISO standard, and I'll mention that briefly, but as MERV numbers get larger, the filters are more efficient overall, and they do better, particularly at small particles. There are 3 rating ranges, 0.3 to 1 micron, 1 to 3, and 3 to 10, and minimum efficiencies are established in each of those ranges. So right now, the filters that are specified in minimum standards are at about the MERV 6 to 8 level, and 13 is where we need to get to for a number of reasons that I'll talk more about here in a bit. These figures, I actually put this in at the last moment since it was mentioned. They show the typical shape of a mechanical filter curve. We have high efficiency for small particle sizes because of diffusion. The particles wander around a lot and run into filter fibers. And at large sizes, collection's efficient because of impaction. So inertia will carry particles into fibers, and in between there's a dip. So when she was talking about 0.3 microns and 99.97% for a HEPA filter, that's practically a flat line at 100% on this curve. So the minimum filter efficiencies that are required by ASHRAE's ventilation standards are MERV 6 for residential and MERV 8 for non-residential, and you can see the minimum requirements for each of the 3 rating ranges in this table. Nothing for MERV 8 for 0.3 to 1. You can have no collection there and still have a MERV 8 filter, 20% from 1 to 3, and 70% from 3 to 10. That's not good from a number of points of view. We'll actually talk about other factors than infection first. One concern about those filters is they don't really collect particles that can be inhaled deeply into the lungs and cause all sorts of respiratory diseases. I've overlaid the 3 rating size ranges on the curve that shows the deposition fractions of particles of different sizes in the respiratory system. So this curve is the total, which actually looks a lot like a mechanical filter, doesn't it? And it's because the same mechanisms apply. But if we look at the MERV 8 filter and the minimum efficiency requirements, there's nothing down here in the 0.3 or to 1 micron range. So it's not really doing anything about these particles that will get into the alveolar region of the lungs and deposit and stay there. And not much better for the next range, but pretty good job of collecting the really big particles in the 3 to 10 micron range. So from the point of view of health effects, aside from infection, a MERV-8 filter is not particularly helpful. Now, if we look at infection risk, what we're concerned about is not only that those small particles can be inhaled, but also that we would like to remove respiratory aerosols from the air before we inhale them. And so again, we can overlay the rating ranges on the distribution of droplets that's produced by various respiratory activities. Speaking is shown in the bottom curve and coughing in the top. This heavy black line represents a best fit to a lot of data that was done by Johnson et al. A few years ago, and it's generally considered to be the best available. So again, if we notice that most of the respiratory aerosol particles, and these could contain 50 to 90% of the viral load, are between about 0.5 and 5 microns, and then look at the efficiencies of a MERV-8 filter, nothing in this 0.3 to 1 range, 20% here where most of the droplet nuclei are, it's not going to do a very good job of protecting us from infectious aerosols. So again, where we need to go is to MERV-13, which has a 50% efficiency minimum, 0.3 to 1, 85% from 1 to 3, and 90% from 3 to 1. This is somewhat like an EPM1 50 ISO filter. We don't use that system really in the US, so I generally don't talk in those terms. But so what we find is that from the point of view of infection control, based on some work done by Paro Mazimi and Brent Stevens a few years ago, MERV-13 looks pretty good. This is a figure from a paper that analyzed the reduction of risk of influenza, either by improving filter efficiency or by doing more ventilation. And the chart shows the annual cost for a 500 square meter building for various relative risk reductions. And what we see is with a very small increase in cost, a big reduction down to about MERV-13 for increasing filter efficiency. And after that, when you go to higher efficiency filters, particularly beyond MERV-14, you're mainly adding cost and not much more performance. But that's if you are, these are central filters. I'm not talking about standalone devices. And we also noticed that ventilation in every location that was considered, because of the energy cost, is much more expensive. So filters are a good way to reduce infection risk and probably more cost effective than more ventilation. The other reason to use filters of higher efficiency, as I mentioned, is because of the other health benefits. So another interesting study that I like to show in my talks was this one done by Montgomery et al. From University of British Columbia, and they did calculations of the annual morbidity and mortality benefits of using various MERV rated filters based on the outdoor air PM profile. So each of these curves on the left represents a different city, and we have Delhi and Beijing at the top, which have really bad PM problems in their outdoor air, and at the bottom, pretty clean cities like Vancouver or Sao Paulo. So if we use typical MERV filters like a MERV-8 that's in 62.1, even in the worst case, we're only getting about $100 per person per year in benefits. And if we increase to MERV-13 for Beijing, that goes up, for Delhi, that goes up from about $100 per person per year to almost $600. And that's because the MERV-13 filter is taking out particles that have health effects. And even in the cleaner locations, we see that there's a significant increase when we go from the MERV-8 range to the MERV-13 range for cities that have air quality like you might find in a Western European or US city. So better filters are good, period, at least better than the ones that we're using now. Sonia went through a lot of different air cleaners in her presentation, and I had already decided not to do that, but I just listed here how many of them there are now. ultraviolet germicidal irradiation is certainly the best documented, really the only one that ASHRAE will support in terms of having an evidence basis that it's effective and safe for microbials. We have other air cleaners that are well tested, not so widely used, like sorbents for gases, and there are air cleaners that use different means to remove particles, like electrostatic precipitators and improved fiber filter media. But then we have this whole class of reactive species air cleaners that was discussed in quite a bit of detail: photocatalytic oxidation, dry hydrogen peroxide, bipolar ionization. These are all air cleaners that put things into the air, and so you not only have concerns about are they effective, but concerns about are they safe, because hydrogen peroxide is certainly a toxic gas in higher concentrations. So that the problem with all of these at the moment is that we don't have good methods of tests that are relevant to applications for them. We don't have a lot of peer-reviewed independent data that they're effective, and we also don't have that kind of data that they're safe. In most cases, we're relying on manufacturers' commissioned laboratory research projects to make claims about how they perform. And in many cases, if you actually look at those studies, they are not very relevant to application conditions. Of course, we have lots of other air cleaners that have multiple things in them, combinations of these various modes. That they all can be used to improve air quality, and I'll discuss that in a few moments, what the general approach might be. So the one that we believe is reliably known to work is germicidal ultraviolet light. Sonia mentioned that the standard technology is mercury vapor lamps. It still is. It'll be displaced someday by LEDs, but for now, because of the limitations of output and lifetime of UV LEDs, mercury vapor lamps continue to be the main source. It damages DNA and RNA. Here's a strand of DNA, and this shows thymine dimers being formed by the impact of photons on the bond between thymine and adenine. None of that damage will prevent microbial reproduction. We know that the performance of germicidal UV is very good against coronaviruses. We actually had data on SARS and a number of other coronaviruses before the pandemic started, and now studies on SARS-CoV-2 have indicated that it's just as susceptible as other coronaviruses that have been studied. So by just a good luck, the 254 nanometer UV that's produced by mercury vapor lamps is pretty close to the maximum efficacy of UVC, at least in the range that's traditionally been used. When you go to shorter wavelengths, actually this curve starts turning up again, and the mechanism of disinfection is different. So we have some interesting emerging technologies that may change applications quite a bit. LEDs that can produce wavelengths that will disinfect but are not harmful to humans, and also another class of sources is krypton chlorine excimer lamps, which produce 222 nanometer UVC, and a lot of preliminary studies have indicated that because it's got a shorter wavelength and doesn't penetrate the skin, it doesn't cause the sunburn-like irritation that 254 nanometer UVC does, or the eye irritation. It hasn't been approved for unrestricted use yet, but when it is, and it probably will be, it would be possible to illuminate both the occupants in a room and the air and do air and surface disinfection safely. That's still in the future, although it is being applied to some extent to do that, but you have to observe dose limits if you do that. UV can be applied in a number of different ways. The one that actually works best and is mainly recommended during the pandemic is upper room UVGI, which involves putting fixtures above the occupied zone to avoid causing harm to the occupants and creating a disinfection zone. And air circulates from the occupied zone up into that disinfection zone, and we can get the equivalent of 10 or 20 or more air changes per hour of uncontaminated air if there's enough air circulation. So this works very well with mixing ventilation systems. But it's expensive. It's certainly the most expensive way to use UV. We can also put it in air handling units where it can disinfect recirculated air up to a clean air delivery rate equal to the recirculated air change rate of the system. So you may only be limited to 5 or 6 air changes at most. And if you have a variable air volume system, as many are in the US, then much of the time the clean air delivery would be a lot lower than that. But these systems also have the advantage of keeping cooling coils free of microbial slime and also the condensate pan. So it can also do the duty of reducing maintenance costs and prolonging the life of the coils, and it saves energy as well. I did an ASHRAE research project a few years ago that you can look up. The report's available free to any ASHRAE member, and we found this to be quite effective. If you're going to do air disinfection with air coming by at a high rate of speed, what would be something like 2.5 meters per second if I'm doing the conversions right, 500 feet per minute, you need a higher level of irradiance in this region than it takes to disinfect the coil. So systems that are installed only to disinfect the coils are probably going to be underpowered in terms of being able to do single pass, high efficiency air disinfection. And UV is also used in room disinfection applications in occupied spaces with UV robots like this being wheeled into rooms, and in 15 or 20 minutes they will do a pretty good job of disinfecting. They're used quite a bit in healthcare applications and have been shown to be pretty effective against health care acquired infection pathogens. And they're available in portables as well. So we've talked about outdoor air and mechanical filtration and air cleaners. What do we actually have to do to be safe? And that's something that we hadn't thought about very much before. Maybe this sort of analysis had been done for healthcare standards, but now we're applying the same methods of risk mitigation to other types of buildings. And something that's figured very prominently in the pandemic has been the Wells-Riley model of infection, which relates probability of infections to the amount of infectious material being produced, measured in infectious quanta, which is a surrogate for an actual dose response model. How many viruses do I need to inhale into my lungs to become infected? And what is the production rate from an infected person? We could merge those into one number, the infectious quantum, which is a single infectious dose. So that will increase risk. The breathing rate of susceptible individuals and the amount of time that they're breathing infectious aerosol will increase probability, and we can reduce it by providing uncontaminated air to dilute the source. So that the key design calculation here is what is Q in this equation to get the P that I want to have. However I'm defining that, it may be a very low conditional risk of infection for one person going into a space, or it could be based on reducing the basic reproductive number, the R naught of a community, to less than 1, which will stop a pandemic. But however that problem is formulated, we can calculate what the clean air delivery requirement would be. And then we can take that and generalize the concept to say that I know how to calculate the clean air produced by a filter. It's the airflow rate through the filter multiplied by its single pass efficiency. And we can do similar calculations for upper room UVGI or for other air cleaners. So if we put the Wells-Riley equation in a form where we have air changes replacing a cleaner delivery rate in, say, liters per second, we can add together air changes from all of our controls to get a total that helps us meet this risk reduction target. So if I've determined what Q should be, then I can add together the air changes for actual ventilation and for air cleaners and for filters and even for inactivation by humidity control and deposition. And that's what we're doing in our task force right now, and we're pretty close to having ventilation recommendations ready to publish, hopefully within not more than a month or month and a half, although I can't promise. We're working hard on it. So that's kind of where we've gotten to, and I think we've developed a lot of tools that will be useful in the future, certainly from the point of view of evaluating infection risk in buildings and doing something about it. Let's go back to the definition of acceptable indoor air quality and now look forward a little bit and say what should be acceptable in the future. And I think one aspect of acceptability should be that we have air quality standards that promote health and wellness. We can't guarantee health, we can't deliver health and wellness, but we certainly know that if we don't do a good job with indoor air quality, that we can cause harm to health and wellness. So the concepts of healthy buildings and wellness really need to be in our thinking as we continue to develop even our minimum standards, because we know there's a tremendous cost being paid for operation at the level of the minimum standards that we have. The other piece of acceptability, I think, needs to be resilience. So we need to have standards for indoor air quality in all buildings that say something about how systems should be prepared to respond when we have something like an epidemic disease outbreak, or when we have wildfires or other types of events that may make outdoor air less suitable or unsuitable without treatment for ventilation. So if we do those two things, there would be tremendous change in the quality of indoor environments in our buildings, and we would reap large societal benefits from the reduced healthcare costs and from extended lifespan and other things of the sort that I've mentioned. But we were really only weeks into trying to deal with the pandemic when we started to get questions to the ASHRAE task force about what about the energy impact of all of these things that you're recommending. At the time, we were recommending maximizing outdoor air, which we no longer do. You should look at the ASHRAE core recommendations and see that we've really changed the approach to be one that is much more flexible. So we need to have not only health and wellness and resilience, we also have to have sustainability, because we can't throw away our goals for energy and environment in the course of trying to make buildings safer and healthier. So some of the things that we should think about in the future is design for flexible operation. We don't want to build permanently into our systems capabilities that aren't needed except under extreme conditions. So we don't necessarily need to have high rates of ventilation all the time. We may need them from time to time when there's an epidemic. Same thing with air cleaners. We don't necessarily have to operate a UV system all of the time. So we need to do some good thinking about how to, without greatly increasing the first cost of buildings, make it possible for them to adapt. That's a good thing for you to think about and discuss. Efficient ventilation is, of course, another important area. Energy recovery will only become more mandatory and more sophisticated and efficient in the future, and that will help. Another thing we can do is focus on efficient air distribution. Right now, even with displacement and underfloor systems in many buildings, we do general ventilation when we could be doing local ventilation or personal ventilation. So we should look for opportunities to deliver clean air only where it's needed, and to allow air quality to be lower where there aren't occupants spending much time or in unoccupied spaces. And certainly in the parts of the world that have focused on mechanical ventilation and mechanical heating and cooling, looking at hybrid ventilation systems to try to get more benefit from using outdoor air for cooling will be another way that we can reduce energy use. But beyond that, I think alternatives to ventilation are really going to be a key to this sustainable, better indoor environmental quality future. And this is why it's such a problem that we don't have the standards that we need for certifying a lot of the air cleaners that are coming out. If we did, then we could apply them very effectively so that we did not have to increase outdoor air much or at all above minimum ventilation rates, and we could still make buildings a lot safer and healthier for the occupants. And I think a fourth key to the future is combining smart technologies with healthy and resilient concepts. So one of the needs here is sensors. We have sensors for some indoor air contaminants and not for others. Biological contaminants is one of them for which we don't really have good sensors that can be used as part of a control system. Cost tens of thousands of dollars for a system that will just tell you when there's SARS-CoV-2 in a space, but it certainly isn't something that could be used for control. And I think that the concept of demand control needs to be enhanced, and the focus needs to be not as much on simply minimizing energy use by driving ventilation down to the minimum standard, but by using demand control to identify where people are and to deliver a high level of indoor environmental quality to them. So both spatially and temporally in our buildings to localize our energy use. This can also be done with more distributed systems that go zone by zone instead of treating large areas of buildings. Occupant interactive controls are another way to get to this. One of the interesting concepts I ran across in putting together a talk on the development of smart technologies is that we've moved beyond the fully automated building, which was the building that does everything for the occupants, to a concept of a smart building or an intelligent building that makes use of the occupants in appropriate ways to help control conditions. And this is, I think, the future we're headed towards. And finally, energy optimized emergency operating modes is another thing that we can do. So a few final thoughts here, just to summarize. As I noted at length, we've been aware that our buildings have IAQ issues for a long time, and our standards don't help us prevent or address them. Also, we have technologies today that are capable of solving most of our problems. There's nothing really missing between ventilation and filtration and the tested air cleaner types that we have. We can do a lot with those in terms of controlling exposures. There are some emerging technologies that will help, but some of these technologies that are being discussed now are going to fail, and it may take some time to really get to the point where we have the ability to sense and in real time control all of the contaminants that we'd like to. Standards are definitely going to change. I want to point out that the ASHRAE task force is not a standards writing body. We're writing emergency interim guidance, and it shouldn't be mistaken for changes to standards that are made by the consensus process. But the changes will come, and two things to say here. We shouldn't rush to make changes because we're talking about permanent changes to how buildings are designed, and it's very complicated, and we need to evaluate all the data. But the other thing is that we must not delay either, because the farther we get downstream from an event like the pandemic, the easier it will be for everyone to say, well, that wasn't so bad, and it only happens every 100 years, so maybe we don't need to do something. I think we need to maintain the sense of urgency and importance of this experience long enough to actually put those lessons to good use. And again, our overall goal needs to be better IAQ plus resilience plus sustainability. And the final note is, unfortunately, the pandemic is not over, so please do look at the guidance that ASHRAE has published at ashrae.org/COVID-19. And if you want to read it all on one page, these core recommendations summarize the main points were approved by the task force at the beginning of January, and they're posted at that page for you to read. And with that, I'll thank you for your attention. I've gone a few minutes over my allocated 45 here, but I'll be happy to have some discussion and answer questions now. Thanks a lot.
Thank you very much, Professor. Thank you very much. So also, as you can see, we have Dimitris in our company as well. And we're going to have some questions by the usual suspect, Alkis.
Yeah, I'm that guy. I know. Sorry about that, Bill. Things tend to pop up in my head every now and then, so that's why I'm asking you. So I remember you mentioning something about the UV. I've seen some studies for the UV lamps before the coils, that they keep them clean and everything. And I think I've read somewhere in a journal maybe that they also decrease the low delta T syndromes that you may have on coils. Is that a fact? Have you seen that in numbers?
Yeah, and you may be talking about a paper that my PhD student Joe Firentello and I published with Chandrasekhar and his PhD student a few years ago. And so yes, if what UV on the coil does is increase the air side heat transfer coefficient. So if you have a higher heat transfer coefficient, you get a larger delta T and you have a lower flow rate requirement through the coil. It wasn't a big impact, but it was slightly beneficial. And it did have some pumping energy impact and some impact on the chiller. The main impact is on fan energy consumption, as we were seeing 10 to 15% reduction in pressure drop at a given flow rate, and that would more than pay for the operation of the system in the year. There was a net energy savings, particularly in climates where the coil is wet all the time. That's where the big benefit is. So instead of having cycles where the coil fouls and then you clean it and fouls and you clean it, and every time you clean it, you pack more stuff into it that you can't get out, and it gets worse and worse over time. I've been told by people who've been using coil disinfection systems for years that the coils look the same after 15 years as they did when they were installed.
Well, this actually sounds fantastic, and if it actually does pay on for itself, like it has a ROI, a return of investment over a few years or months, I don't know how long will it take, then it kind of makes sense in the sales point of view as well. That's not only to disinfect them, but to save some money out of it, because all we hear from now is money spending for UVs, for HEPA, for increasing, and it makes sense. This is a pandemic, but this is one of the very few things that it also saves you money. So this is why I would like to point that out.
Yeah, well, I think things that save you, let's say, healthcare costs if you're a business, or that allow you to occupy your building that don't require increases in ventilation are important too. And so when we talk about HEPA filters requiring a lot of power, if we're deploying some portable HEPA filter units rather than increasing outdoor air, I think the net on that is probably a pretty big energy savings. I forgot to address the question about air changes. You know, the most widely circulated reference point for how many clean air changes do we need is 5 to 6 being recommended for schools in the U.S. based on some Wells-Riley model analysis. What I've seen of what our team that's working on ventilation rates has been developing is that we're probably going to come up with recommendations that are no worse than that. Actually was a little bit surprising. When you take minimum ventilation and MERV 13 filtration into account, in a lot of buildings you don't have to increase the clean air delivery by a lot over what's already provided. It makes a significant difference in risk reduction, but it's not huge increases in a lot of cases. It really depends on how high the base ventilation rate is. Some types of buildings have very low air changes and others have higher because of the occupant density.
It makes all the difference, because with MERV 13, we in EU, in Europe, our minimum filtration is MERV 13. So for us, this is an even extra bonus thing. Our minimum filtration for buildings is MERV 8 and MERV 13 in conjunction. So we have the minimum filtration is MERV 8, 7 or 8 for the returner and the outdoor air, and in the supplier of the units, if are DOA, we have MERV 13 as a minimum requirement.
You know, I think that was a really interesting difference between REBA guidance and ASHRAE guidance. We have so many recirculating systems in the US, VAV systems, and it seems much more common to just have once through ventilation in Europe. So hence the recommendation of no recirculation, where we kind of rely on it in the US. You look at our healthcare standards, and we have 12 air changes of recirculation with MERV 14 filters for infection control in spaces. But if you're going to have recirculation, you'd better have good filters as well. The other thing about 100% outside air is that the filter in that unit doesn't do anything for infection risk. It's great for outdoor contaminants, but if you're going to control indoor contaminants, you have to put other controls into the spaces.
Not all units are 100% dedicated outdoor air. We have air handling units that they may work 100% fresh air depending on the weather outside, and then they can go up for a maximum, I don't know, mixing of 30 or 50%, depending again on the energy scenario. But again, the minimum filtration for that is going to be MERV 13. But what's most important is that we have a lot of outdoor air in our units because of the European standard for the heat recovery. So our minimum heat recovery on heat exchangers is 79, 80%. So we cannot have an outdoor air unit without a heat recovery of 80%. And this helps us. There's nothing being sold or made within EU. So with that being said, it's easier for us to have a lot of fresh air and more fresh air because it costs less in terms of energy as well.
Yeah, I don't think I have anything to add to that except that the heat recovery requirements and economizer requirements in 90.1 keep creeping up. So it is becoming pretty universal that you have to have very good energy recovery, and that's a good thing.
Yeah, the decarbonization part of Europe has been ahead for more than a decade now. It's been implemented from EU into all the countries. So Kostas Ballaras knows that for a fact for all those decades. So it's mandatory for us. You're not even allowed to buy anything from a pump that has to be inverter, absolutely inverter, or from a boiler that has to be condensing, absolutely, or you cannot sell it in the EU or buy it or make it. So there are a lot of regulations on the decarbonization side of Europe that were pretty ahead exactly because of our legislations.
You know, as I've been thinking about this whole issue of energy consumption versus IAQ, I just come to believe, although I'm not a huge fan of lots of controls, that wasting energy on unoccupied spaces has got to be one of the biggest factors. Seems to be that China that has already made that decision that you save a lot of energy by just turning things off, and they're developing a preference for single zone systems, lots of them, instead of big centralized systems.
Yeah, that's one way to go. Although the single zone systems, there's another thing, and we've been dealing with that, especially in my country, in the new legislation that we have for the buildings, that the single zone systems are very low in terms of technology for sensors and for dehumidifying, and they're HRV units. They are not air handling units, so you cannot dehumidify and reheat. You cannot do such things when you go to zoning on a zone basis. And this is another thing. So the automation and the amount of dehumidification that you have and all those things.
Yeah, well, and of course that's another example of how we just need to look at familiar things from a different point of view. A rooftop unit, the only thing that came to mind when anyone thought of a rooftop unit was cheap, because that was what they were designed for. But if we want to have them be high performance, we can certainly make them high performance, although that will change the economics quite a bit.
Exactly. That's a very good point. Exactly. Dimitris, you were saying?
I add some remarks. Thank you, Bill, for coming. Your presentation is always an exciting one, and it's glad to have you again, and we'll see you theoretically, physically in summer, in September, in the Indoor Air Quality 2020.
I'm certainly
And
counting.
it's not a typo. There are a few questions that I had that you did answer them. One of them was that hopefully results from the task force, from the epidemic task force, will be taken into account with the standards committees and be implemented sooner rather than later. Perhaps we need to rethink the design of buildings, especially large buildings, have safe passageways, perhaps have sensors that can detect. I'm not knowledge of any sensors for COVID nowadays, but I think that eventually we will have ways to trace it, because pandemics won't go away from our lives. And I hope that the task force won't go out of phase, out of fashion, after a short while, when people are relaxed again. And I definitely feel that we need to keep this initiative going for as long as we can.
The original plan was to end it this June, but I think we've already recognized that we're having too much impact and there's too much need to have that focus to sunset it this early.
There was a discussion way back in 2014 with the now Vice Admiral Bamblenis on an outbreak in a cruise ship, and what you do when you have such a thing, that you can contaminate easily through the ventilation system all the occupants, 2,000, 3,000 passengers, how many? So this conversation needs to be open, and hopefully we'll continue this in September, that we'll have more time.
Yeah, I would welcome the opportunity. Yeah.
Yes, that's all for me, and we'll try to find solutions to things that are obvious but unthinkable. Anyway, Titus, if you want to add something, and then we can proceed to our next speaker.